Okay, so the lab that we're going to do next it's rare that we use computer simulations, but this is going to be one of them. Mainly because it's difficult to get the board to approve us building our own spaceship and going to the moon and actually landing on the moon.
So difficult.
Oh, it would be, don't get me wrong. They won't even give you a particle accelerator, so.
Why?
I know.
Okay, a cyclotron is
But then
It's
again,
like, the only high school in the United States with our own particle accelerator.
a cyclotron is not that bad.
I know. What can it possibly?
Well, I mean, it's
Okay, anyway.
it's not that. It's not
Back to our story.
big.
So, when we're gonna look at we're gonna start off with what's called, there used to be, and it's been retired, the space shuttle. And that was like the go-to workhorse for getting satellites into space and astronauts into space. They had some mishaps along the way that were not good at all. And I can remember both where I was in both situations, and I heard the news. The first one, when Challenger blew up, I was a freshman in a Chem 1 lab at Butler County. And the second one that burned up on entry, I was out, it was Saturday morning, I was out working in the fields. So, yeah, space definitely has its own challenges. But all of these are like the ultimate manifestation of this whole concept that we've been talking about. Newton's first law, second law, third law of motion. So this video goes through and it talks about the space shuttle, it uses that as a reference. But it's the same idea even now. Basically, when you look at rockets, you have two options. You have what's called a solid rocket fuel system. Both of them have their advantages. So solid rocket fuel systems work well because it's kind of like a Roman candle. All you have to do is light the fuse and it's going to blow up, okay? But the disadvantage of solid rocket fuel boosters is that once you light them, there's no off switch, okay? Once they start to burn, you can't shut them off. All you can do is direct the outflow from the exhaust. But they're simple, okay? Light it, boom, you're done, okay? The second option is, and this is like what you should see here with the Saturn V rocket. So Saturn V rockets, they used pumps to combine fuel, kind of like the carburetor, the fuel injection system in your car. And there's various fuels you can use, like for example, you can burn hydrogen and oxygen, okay? So that's one of the things that the space shuttle did. But it was liquid hydrogen and liquid oxygen. And which is cool, literally, very, very cool. Liquid hydrogen is the second coolest liquid on Earth. Anybody know what the coldest liquid on Earth is?
Liquid nitrogen?
Nope, nitrogen actually is relatively warm. Alex?
Helium.
Liquid helium. Because basically if you want to take a gas and change it into a liquid, gases aren't, this is not scientific, but you get the point. Gases aren't very sticky. That's why they exist as gases. If they were sticky, they would be liquids or solids. So basically, you have to slow them and get them cold enough so that when they run into each other, they stick. So liquid oxygen, and this is a whole lecture in AP chemistry about something called London dispersion forces and intermolecular forces. So basically, the bigger the molecule is, the stickier it is, the easier it is to get it to condense. Liquid oxygen, pretty easy to do. Liquid hydrogen is tough because hydrogen is so small. So it's not very sticky, so you have to get it really, really cold before you can get liquid hydrogen. So with the space shuttle, it's unique because it combines both systems. It combines the solid rocket boosters and it combines the pumps that run liquid hydrogen and oxygen when they combine. So the advantage of pumps is that you can, just like the carburetor or your car, you can press down on the gas pedal. You can give it more fuel, you can give it less fuel. If something goes wrong, you can shut it off. But it's more complex. So one of the things they'll talk about on the space shuttle engines that run hydrogen and oxygen, and this is the challenge. So you have pumps that have to handle liquid hydrogen, the second coldest liquid on Earth. And if you've ever worked with machinery or metal or anything when it's cold outside, that's a whole new challenge. Metal gets brittle. When metal gets cold, it contracts. Things freeze up. So you have the pumps that have to handle these exceptionally cold liquids. But when those liquids ignite and you produce all of this thermal energy, that thermal energy raises the temperature high enough to boil iron, okay? Not melt it, not make it glow red. So if you've ever seen water boil, imagine that we're going to put a chunk of iron into a pot and we're going to heat it up so much that the iron begins to boil. So within the same system, you're going to go from the second coldest liquid on Earth to temperatures high enough to boil iron. That's a huge engineering challenge. Then how do you control that explosion? Because that's basically all it is. It's a controlled explosion. Because if you don't control it, very bad things happen. And then you get into, okay, well, then how do you navigate? How do you, once you're in space, how do you keep track of things? You really don't have fixed points. So what this video is going to do, we're going to stop and talk along the way, but this is just going to kind of give you some background for what we're going to do in terms of the actual lab and trying to do the calculations and land in a simulation, the lunar excursion module on the moon. So the video is not bad, so here we go.
Oh.
Few decades, accomplishments in spaceflight have proven to be some of man's most
That's the Apollo
triumphant achievements.
missions right there with the Saturn V rocket.
The underlying principles
That's
which
spatial.
made these achievements possible came as a result of hundreds of years of investigation into the behavior and structure of matter. It's these principles of physics which play the foundational role in making spaceflight a reality. The launching of a rocket provides a spectacular display of force and energy. From a physics viewpoint, a rocket launch vehicle can be thought of as a large force machine. Its sole purpose is to apply a continual thrusting force in order to produce an acceleration. If the rocket is to achieve a low Earth orbit, the magnitude of the acceleration which is required tends to be quite large. The rocket must go from a state of being at rest on the Earth's surface to that of traveling 8,000 meters per second at some given distance above the Earth.
That's about 5 miles per
This
second.
tremendous velocity
And later
change
on,
takes
we'll know
place
why
over a
that has
relatively
a
short
specific
period of
number.
time and necessitates the large amount of energy and acceleration provided by a rocket launch vehicle. The single most important component
So
of a
that
launch
gives you some
vehicle is the rocket
perspective.
engine.
This is a Saturn
Use
V
of a rocket
rocket that
engine
got us
provides
to
the
the
means
moon.
by which thrust
So
is
there's
produced from
a
the
guy
vacuum of
standing
space.
beside it.
Since oxygen is not present in the space environment, an oxidizer must be carried on board the rocket along with the fuel. The space shuttle's propulsion system is made up of 5 different rocket engines, 3 main engines which use liquid propellant, and 2 rocket boosters which use a solid propellant. The tremendous temperature extremes which the space shuttle's liquid propellant main engines operate at required innovative engineering during their design. The engine's complex system of precision valves and pumps must handle the extremely cold propellants without freezing up. The liquid hydrogen fuel at minus 253 degrees Celsius is the second coldest liquid on Earth.
Yeah, minus 253.
However, when burned with liquid oxygen, the temperature in the engine's combustion chamber reaches 3,300 degrees Celsius, a temperature higher than the boiling point of iron. In the combustion chamber of the rocket engine, the propellants are consumed in a combustion reaction. The thermal energy generated from the combustion heats the newly formed gases to extremely high temperatures. These gases, possessing a large quantity of kinetic energy, subsequently go through an expansion in the rocket nozzle and are ejected at extremely high velocities. With the fuel being composed of liquid hydrogen and liquid oxygen, the hot gas which is expelled from the engine is primarily water vapor. The thrust which is produced by the engine can be explained in terms of Newton's third law. As the engine applies a downward force on the gases, causing them to be ejected, the gases
So
must
notice
also
that
apply
doesn't
an
have
equal and opposite
anything to
force,
do
pushing
with the
upward on the
surface
engine.
that is pushing against.
This upward
It's
force
all
pushing on the
within
rocket engine is
itself.
essentially a reaction force to the gases being pushed downward, and is responsible for giving the engine its upward thrust. Newton's second law of motion, expressed in terms of momentum, can be used to find the magnitude of the thrust produced by a single space shuttle main engine.
Now, we'll talk about this once we get into momentum. So this is Newton's second law of motion. You all are used to having mass stay the same, and you multiplied it by the acceleration, which is change in velocity over time. It's legitimate. But if you shift where the change happens, if you shift that to a change in mass per unit of time, and then V is the velocity of the escaping gases, this is how you calculate the force generated by a rocket engine. So if you want to generate a lot of force from a rocket engine, you consume a lot of fuel in a little bit of time, and that gas gets ejected at a very high velocity. And that's what rocket engines do. But this becomes the catch-22. It's like, oh, we need more force. Well, let's build bigger rocket engines. Great. But what do you know about bigger rocket engines? They weigh more. Guess what? What else do they take?
They need more fuel.
They need more fuel. So now the rocket is getting heavier, because now you've got bigger rocket engines that can consume more fuel. So if the gain in force isn't proportional to the increased fuel and mass, there's no point in building the bigger rocket engines, because you're not going to get off the ground. So they'll get the numbers, but these on the space shuttle that burn the liquid hydrogen and oxygen, those burn about 450 kilograms per second, which is about 1,000 pounds per second, which is like the mass of a small car. So each one of these rocket engines is burning the mass of a small car per second. They'll show the solid rocket boosters. Those are burning at about 4,500 kilograms per second. That's about 10,000 pounds. That's the weight of a really, really big truck. So if you combine them, you're at about 5,000 kilograms per second. So that's the rate at which all these engines are burning through fuel.
With the propellant gases being ejected at a velocity of 3,600 meters per second,
Which is about
and at a
10
rate of
times the speed of
470
sound.
kilograms per second, the resulting thrust generated by the engine is equal to 1.7 million newtons. As seen by the second law, the greater the rate at which the hot gases are exhausted, and the greater their velocity, the greater the resulting thrust will also be. Solid propellant engines
don't
make up a
stand
second
behind
group
this
of
one
rocket
and light
engines.
it.
These engines are much simpler in design due to the fact that they require no pumps, valves, or complex propellant feed systems. However, once ignited, they cannot be shut down. The shuttle's solid rocket boosters use a propellant which consists of aluminum powder as the fuel and ammonium perchlorate as the oxidizer. A rubber-based polymer binder is also added. This mixture fills the entire length of the solid rocket motor, except for a hollow channel extending through its center, which serves as a combustion chamber. When ignited, the propellant
Yeah.
burns from the center out
That would
towards the
mess up
sides
the
of the
day.
casing at a nearly constant rate. An extraordinary amount of thrust is
You
created.
can only make that mistake once.
Propellant gases are exhausted at a velocity of 3,300 meters per second and at a rate of 4,000 kilograms per second, creating 13 million newtons of thrust. Enough thrust to maintain the flight of 20 747 airliners.
Higher dude. You're so quiet.
The space shuttle system is the most technologically advanced and complex machine on planet Earth. Unlike the Saturn V rocket, which carried its payload to the moon, the shuttle is designed to attain a low Earth orbit. Achieving the necessary orbital velocity is no small task, as it requires the combined thrust of the shuttle's 3 main engines and 2 solid rocket boosters. With the large external tank storing the liquid propellant used by the main engines, and the 2 solid rocket boosters containing their own solid propellant, the total mass of propellant aboard the shuttle equals an enormous 1.7 million kilograms. This propellant mass accounts for 85% of the shuttle's total launch mass, and provides 20 billion kilojoules of chemical energy, which is necessary for attaining orbit. The filling of the liquid oxygen and liquid hydrogen tanks occurs on the launch pad several hours before launch. The oxygen vent arm, which caps the top of the external tank, allows vaporized oxygen to escape from the tank, and thus prevents the tank pressure from building up to excessive levels. A similar arm allows the lower positioned hydrogen tank to also be vented. As the final countdown
The guy on
begins,
the right
the flight crew is taken to
has
the
to be
launch
a,
site
has
and
to be a
enters the
NASCAR
orbiter by way of an
fan.
access
Check out
arm.
those sideburns.
With all systems checking out and working order, the crew access arm is retracted at 7 minutes before launch. At 3 minutes before liftoff, the main engines are swiveled to their proper launch positions. All of the shuttle's engines are mounted on a pivot device, or gimbal, which allows the flow of exhaust gases and the direction of thrust to be controlled during ascent. The oxygen and hydrogen vent arms retract
Yeah,
at
you might
just 2
want to take
minutes
those
before
off
engine
before you
ignition.
try and launch.
At 7 seconds before launch, the sound suppression water system starts dumping 300,000 gallons of water onto the pad. This water is used to partially absorb the 170 decibels of acoustical energy given off by the engines, preventing it from fully reflecting off the pad and causing damage to the shuttle. Hydrogen igniters under the main engines are used to ensure that any hydrogen flowing out of the engines prior to ignition is burned off as it emerges. This prevents the buildup of a potentially hazardous cloud of explosive gas. At 6 seconds before liftoff, the 3 main engines are ignited. Shock waves coming out of the throats of the nozzles cause them to vibrate momentarily. At T-minus 3 seconds, the main engines reach 90% thrust. 1/2 second before liftoff, the solid rocket boosters are ignited as explosive hold down.
Now, why did they start the 3 engines on the space shuttle first before they ignited the solid rocket boosters? Andrew,
You have to give the turbo pumps time to spin up.
beyond that.
It gives time to check for issues.
Yeah, because if those 3 engines that are running on pumps, if there's any problems with them, they can shut them down, okay? Because those have like an on-off switch. If you start the solid rocket boosters first, and there's a problem, you're screwed, because you can't shut them off. Now, even though these 3 engines are firing, Connor S., why hasn't the space shuttle lifted off the ground? You're firing these big engines on the bottom of the space shuttle.
Because the force has surpassed the gravitational force on the rocket.
Beautiful. You haven't paid off the gravity mafia yet. Oh, it looks cool, right? You're firing these engines and smoke and flames and rumble and all this good stuff. It's cool, but you're not going to go anywhere. So that would be like me taking a hydrogen balloon and attaching it to a 200-gram mass like I did yesterday. Is the hydrogen balloon lifting it up? Yeah. Is it going to go anywhere? No. So they're firing, but not going anywhere because of the fact that you do that, so in case there's a problem, you can shut it down.
Bolts are triggered. During the initial part of its ascent, the shuttle's engines deliver a combined power of over 100 billion joules per second. an amount of power which is equivalent to the output of 85 Hoover dams. A distinction can be made between the different types of engine propellant, as the main engines are observed to burn with a clean light blue flame as a result of the hydrogen and oxygen combustion. This contrasts with the solid rocket boosters, which burn with a bright orange flame due to the combustion of the solid aluminum fuel. The dynamics of the launch can be studied in more detail by examining the forces involved during the shuttle's ascent. With the three main engines ignited and applying their combined thrusting force of 5 million newtons, the shuttle still remains motionless. At this point, the upward thrusting force represents only a fraction of the total shuttle weight, which is equal to 20 million newtons. If the supportive launch pad was taken away during this period, the net force would cause the shuttle to accelerate downward. In order for the shuttle to accelerate
So
upward,
look off
the
to the
total
right,
thrusting force
bottom
must be
right, where
greater
they
than the
light the
shuttle's
solid
weight.
rocket boosters.
This takes place when the solid rocket boosters
Boom.
ignite. With the two solid rocket boosters applying an additional 26 million newtons of thrust, the total thrust from all engines is now 31 million newtons. At this point, the net force is directed upward and the shuttle lifts off. The initial upward acceleration can be determined by using Newton's second law of motion. With a net force of 11 million newtons acting on the total shuttle mass of 2 million kilograms, the initial acceleration is equal to 5.
Okay, so here's the heart and soul of what we've been talking about for the last couple of days. The upward force from the engine's total was 3.1 times 10 to the 7th newtons. You got to pay to the gravity mafia 2.0 times 10 to the 7th newtons. So the difference between those two, that 1.1 times 10 to the 7th newtons, that's your net force, okay? Then you're dividing it by the mass, there's your acceleration. Now, this is something that Andrew brought up earlier. Considering the fact that these rocket engines are going through about 5,000 kilograms of fuel per second, if you assume that the force from the engines is staying the same, Andrew, what's going to happen to the weight of that ship?
It's going to get lighter.
It's going to get lighter. So the gravity mafia is going to demand less and less money. So, Andrew, what's going to happen to the net force?
It's going to increase.
The net force is going to get bigger, okay? But what's going to happen to the amount of stuff that you have to accelerate? Thatcher.
It'll decrease.
It'll decrease. So you're going to have a bigger net force on top divided by a smaller mass on the bottom. So what's going to happen to your acceleration? Scooter. It's going to increase. So this is going to sound odd, but your acceleration is going to accelerate. Okay? Because of the fact that you're going to have a bigger and bigger and bigger net force, you have less and less mass to accelerate, so your acceleration gets bigger. Okay? Woo! Yay for physics.
8.5 meters per second squared. With the thrust initially remaining constant, the shuttle's acceleration will continually increase as the engines expel their propellant and reduce the mass and weight of the shuttle system. With 9,400 kilograms of propellant being exhausted every second, the shuttle's mass becomes reduced very quickly. After only 30 seconds into the flight, the shuttle is traveling with an instantaneous velocity of 200 meters per second. At this point, the engines have already expelled 280,000 kilograms of propellant, reducing the shuttle's total mass and weight by 14%. Newton's second law of motion shows that the acceleration has now increased to 8.2 meters per second squared. At approximately 50 seconds into the flight, the shuttle enters a critical period during its ascent as its velocity approaches the speed of sound. As the shuttle moves through the atmosphere, it creates a disturbance in the surrounding air. The resulting pressure waves spread out in spherical shells at the speed of sound. As the shuttle approaches the speed of sound, it begins to catch up to the pressure waves it produces. With the distance between wave crests becoming successively smaller, the waves begin to pile up in front of the vehicle, creating a wall of high pressure. This pressure barrier, sometimes referred to as the sound barrier, presents
Because they
resistance to the
thought it was
shuttle's
like
motion.
literally almost like a
Breaking through this
physical
pressure
wall
barrier creates a
that you
period
had
of
to punch
maximum
through.
dynamic pressure and results in a considerable amount of aerodynamic stress being imposed on the shuttle. To minimize this stress, the shuttle throttles down in an effort to reduce its acceleration at the time of passage through the pressure barrier. After breaking through the barrier, the pressure becomes greatly reduced and the shuttle's motion is no longer impeded. With the shuttle no longer experiencing the high level of aerodynamic stress, its engines are throttled back up to 100%. Now, traveling faster than the speed of sound, the shuttle outruns the sound waves it produces. The resulting pattern of waves leads to constructive interference taking place, where successive wave fronts overlap, forming a single very
And if
large
they
wave
do
front,
this,
which
that's why
carries a
one of the
tremendous
reasons they
amount
do
of
it
sound
on the
energy
ocean.
along with it.
But those sonic
This
booms
large
are
wave
like
is called a
shadow
shock wave
windows.
and forms a conical shell of sharply increased
There's
pressure
that much
with the
pressure.
shuttle at its apex. Throughout the remaining atmospheric portion of its ascent, the shock wave will continue to trail behind the shuttle. After 100 seconds into the launch, the engines have expelled an enormous 940,000 kilograms of propellant, reducing the shuttle's total mass to almost half of what it was at the time of launch. With this decrease in mass and resulting increase in net force, the shuttle's acceleration has climbed to 18 meters per second squared.
So we'll talk more about that later. So if you're in the space shuttle
During
at
this
18
period of
meters per
time,
second
frictional
squared, your
heating
body
caused by
will
the
feel
atmosphere
twice as heavy
reaches its
as it does
maximum
right
level,
now.
as
So
collisions
you're
with
used
air
to being
molecules
under
cause
1G,
portions of the shuttle's
you would feel
exterior
twice as
to
heavy.
reach temperatures of 1,000 degrees Celsius for a short time. At 2 minutes into the flight, and at an altitude of 45 kilometers, the two solid rocket boosters have consumed nearly all their fuel and no longer provide thrust to the shuttle. At this point, the shuttle's weight can be considerably reduced by dropping the spent booster casings. The boosters are released by explosive bolts and are then powered outward and away from the shuttle by 4 small separation motors on each end of the solid rocket boosters. The reusable booster casings parachute back to Earth, splashing down in the ocean with an impact velocity of 18 meters per second. With the solid rocket boosters no longer present, the total amount of thrust acting on the shuttle dramatically drops. During the initial part of the vehicle's ascent, a large portion of the 31 million newtons of thrust was primarily used to accelerate the enormous
It's
mass of
basically
propellant
a
on board the
huge
shuttle.
flying fuel tank.
With most of that propellant now consumed, and the shuttle's mass only 1/3 of what it was at the time of launch, the thrust provided by the 3 main engines is sufficient to maintain the vehicle's acceleration. At 8 minutes into the flight, the shuttle's velocity has increased to 7,000 meters per second, a
Not
velocity
quite
more than
fast
20
enough to
times
orbit,
greater
but
than the
pretty
speed
close.
of sound. During this time, the acceleration approaches 30 meters per second squared,
So now you're
a value
going
which is 3
Gs.
times greater than
So
the
you would feel
9.8 meter per
3
second
times
squared
heavier
gravitational
than
acceleration experienced at the Earth's surface. To the crew aboard the shuttle, the acceleration of 3 Gs forces them back into their seats as they feel the sensation of increased weight. Although the acceleration causes some discomfort and stress to the body, it is less than half of what was experienced by the Apollo astronauts aboard the Saturn V rocket. Cutoff of the main engines occurs at 8.5 minutes into the flight, at an altitude of 120 kilometers above the Earth's surface. 12 seconds after main engine cutoff, the near-empty external tank separates from the shuttle. At separation, a small valve in the nose section of the external tank is opened, allowing pressurized gas from the liquid oxygen tank to escape. The escaping gas applies a rotational torque to the tank, causing it to slowly spin.
Because if it
This
didn't,
tumbling motion
it
prevents
would act like a
aerodynamic skipping
smooth
off the
stone thrown
atmosphere
on the water,
and ensures the
but
correct
it-
re-entry
but
trajectory.
If it didn't, it might like hit the atmosphere.
As the
and
tank
skip
breaks
like a
up
rock.
upon re-entry, the debris will harmlessly impact within the pre-planned location in the Indian Ocean. With the external tank gone, the remaining orbiter represents only 5% of the shuttle's original launch mass. Having spent all of its main engine fuel, the shuttle's orbital maneuvering engines provide the final thrust for orbital insertion. The maneuvering engines, along with the other engines which are used while in orbit, use a hypergolic propellant. Hypergolic propellants are fuels and oxidizers which ignite spontaneously on contact with each other and require no ignition source. This easy start and restart capability
But
makes
you
them
wanna make sure
reliable
they're
and
kept separate,
advantageous
so
for
you want
engines
them
which are
mixed.
used a number of times while in orbit. At 10.5 minutes into the flight, the two orbital maneuvering engines fire to place the vehicle in a low elliptical orbit. The engines provide a total thrust of 53,000 newtons, giving the 95,000 kilogram orbiter an acceleration of 0.56 meters per second squared. The final step in achieving the desired orbit comes at 45 minutes into the flight, as the orbital maneuvering engines fire for a second time, placing the shuttle in a nearly circular orbit at 400 kilometers above the Earth's surface. Having attained an exceptionally large velocity of 7,700 meters per second, the shuttle is able to complete a full orbit around the Earth in only 1.5 hours.
Now, we'll do all those calculations, but when they had that last diagram where they showed it in orbit, that is so far out of proportion. If you consider like the globe that I have up here, which is about yay big, to scale, the space shuttle orbits about half an inch above that globe. So when that diagram, and I'm not faulting them, they just kind of did it, but that was so far out of scale. Only thing you have to do to be in orbit is just be above our atmosphere. There's nothing magic about space. You just can't be within our atmosphere because of drag coefficients with the air. Okay, now we'll talk about getting to the moon.
Sending a manned spacecraft to another planetary body presents an enormous scientific challenge. That challenge is immeasurably escalated by having to also return the manned spacecraft safely to Earth. The extremely successful Apollo missions made a total of 6 different manned landings on the surface of the moon. The lunar module, consisting of a lower descent stage and an upper ascent stage, allowed the astronaut to descend from...
So we'll talk more about this, but if you look at that, you can kind of see like that lower spider leg part. They had 2 distinct engines. So that lower engine was designed just to basically maneuver and safely land on the moon. When they was ready to take off, they severed all the controls and everything with that lower descent stage, and then you had a separate engine for basically that kind of like bug little thing on the top. So the bottom of that is still on the moon. What we brought back with us was the top part of it, because it was just like, why fly that back up? Let's sever it, boom, there you go. So what you're gonna go through is the calculations to get that thing on the moon.
lunar orbit and set down on the moon's surface. This vehicle was a true spacecraft in that it was capable of operating only in the space environment. Having used its descent engine to land on the moon's surface, the lunar module would be required to do what had never been done before: lift off from a planetary body other than Earth. Due to the extremely different physical characteristics of the lunar environment, the dynamics of launching a spacecraft from the moon's surface greatly contrast the dynamics of an Earth launch. The black sky during the daytime bears witness to the fact that the moon possesses no atmosphere to scatter sunlight. Because of the lack of any atmosphere, aerodynamic stress and frictional drag are non-existent during a launch from the moon's surface. In contrast to Earth launches, streamlining of the spacecraft becomes unnecessary, as the lunar module's protruding components and non-streamlined configuration is of a functional design and presents no problems during launch. In order to provide the thrust required to lift off from the surface and attain lunar orbit, the ascent stage of the lunar module possessed a single rocket engine. Because there was no backup engine and no other
Yeah,
means to lift
either
off
that
on the
thing
moon's
worked
surface,
or it
a
didn't.
malfunction could
There
absolutely
was
not be
no,
tolerated.
hey, we'll
The single engine
come
had
get
to
you or
work.
call AAA. No.
The engine used the most reliable propellants available, hydrazine and nitrogen tetroxide, two compounds which spontaneously ignite upon contact with each other. Because the
Just
gravitational
keep them
acceleration of the
separate.
surface of the moon is only 1.7 meters per second squared, the 5,000 kilogram ascent stage has a weight of only 8,500 newtons, a weight 6 times smaller than that which it would have had on the surface of the Earth. Because mass remains constant throughout the universe and is not affected by gravity, the spacecraft's 5,000 kilogram mass requires the same definite amount of net force to achieve a given acceleration.
Okay, so that's gonna be one of the key things that you need to understand. When you look at net force equaling mass times acceleration, that is mass. It's not weight, it is mass. So if I've got a 5,000 kilogram spacecraft on Earth, and I have a 5,000 kilogram spaceship on the moon, or a 5,000 kilogram spaceship in deep space, and I want it to accelerate at 2 meters per second squared, I take 5,000 times 2, I'm gonna get 10,000. So the net force that I need, no matter where I am, to get that 2 meters per second squared, is gonna be the same, 10,000 newtons. But that's gonna be harder to do on Earth because of the fact that Earth has such a large gravitational pull. So that 5,000 kilogram spaceship on Earth is gonna weigh about 50,000 newtons. So I'd have to generate at least, more than the 50,000 newtons of force to get that thing off the Earth. Now, on the moon, it weighs about 9,000 newtons. So to get the same acceleration on the moon is easier because it doesn't weigh as much. Okay, stop you on the camera, Andrew. So one